right? Okay, so if, so notice that f a differentiable at P implies that the Jacobian of f is an element of the regular representation of the algebra. I mean, it's technically Jacobian of f evaluated at the point, right? Fine, but if you don't mind, I'm going to drop that point because it's obnoxious. You're like, great, dropping the points again. Now, what does that mean? Jacobian of f at P. All right, so let's think about that. That means that we can write the Jacobian like this, right? Or, I mean, another way to say that, by the way, would be that the matrix representation of the different, how to say that? Well, the matrix representation of the differential of P on the identity should be equal to, you know, the Jacobian of f. What I'm trying to say is the Jacobian has to be in the regular representation, right? And so that means that this Jacobian has to also look like this, right? Again, I'm assuming here that the you know, one is the we can talk about what these equations look like when one is not the identity. Just a second here. There's another way to do this, but I want you to take a look at this equation we have, right? And tell me what you see from it. Like, what do we get? I'll do the easy part. Well, the useless part. From this equal to that. From first columns matching, we get nothing.
Yeah, second columns you get
Mm-hmm.
partial f divided, or partial f of x2
Uh-huh.
is equal to the partial f of x1 times e2.
Times e2, all right. That is called the Kosher-Riemann equation.
Spell it.
So this is one of the A Cauchy-Riemann equations. I mean, it's in vector form. Oftentimes, when people talk about the Cauchy-Riemann equations, they break it down into scalars, but there's the vector version of it. And this continues on. Partial f, partial x n is partial f, partial x1 times en. So there are how many of these? N minus 1 vector equations, right? These are vector equations. So count it. How many total scalar equations is in the green? Each one of these is n scalar equations. You have n minus 1 of them. So this gives us a total of n squared minus n equations. Because n times n minus 1 is n squared minus n. Now, remember these equations, they are describing that subspace of the set of all matrices, which is isomorphic to the algebra. Remember, that's n-dimensional. So think about it. You've got an n-squared dimensional context. How many equations do you need to fix an n-dimensional subspace? Well, n squared minus n. So for an n-dimensional algebra, we're going to have n squared minus n Cauchy-Riemann equations. Yes, in general it's a lot. However, when n equals 2,
It'd be 3.
oh, n equals 2 is 4,
Oh, yeah, 2.
just 2. So what does this I just wrote look like in the context of just, for example, complex case?
Partial FA?
Let's see here. So partial f, let's use x plus iy as our variables.
Okay.
So
Yeah, partial X.
partial f, partial x2 would be, like x2 would be y.
Yeah.
Partial f, partial y is partial f, partial x
E2.
times e2, which is I here.
Yeah.
In other words, it's I times partial f, partial x. That's these are the Kosher-Riemann equations in vector form. Now, this might not be recognizable to a student of complex variables who's learned things with scalars. In terms of scalars, if we let f equal to u plus iv, as is often done, then this gives us uy plus I vy is equal to I times ux plus ivx, which gives us that uy plus ivy is equal to, excuse me, minus vx plus iux. So equating this has to be equal to that, and this has to be equal to that. Those are the usual Kosher-Riemann equations we teach complex variable students, like uy equals to minus vx, and vy equals to ux. These are the famed Kosher-Riemann equations of complex analysis. But at a vector level, what they amount to saying is that you can partial differentiate with respect to y. Well, you might as well just multiply by I the partial derivative of f with respect to x.
One more time.
So these Kosher-Riemann equations are equivalent to saying that you can trade the y derivative of f for I times the x derivative. The Kosher-Riemann equations for hyperbolic numbers, what do those look like? So like if we go to the hyperbolic numbers, x plus jy,
It'd be very similar.
similar. This time we get partial f,
Yeah, it'd be,
partial y.
It would be equal to J partial F partial X.
Right. And so if you just think back, there's other ways to do this. So like the Jacobian matrix, it's ux, vx, uy, vy, right? That's what, this is just the generic Jacobian matrix of, like a u comma v function. And if you think about that matrix satisfying the pattern of the regular representation, what does that tell you? Like if you remember what the regular representation of the hyperbolic numbers looks like?
A, B.
Yeah, I somehow don't. Exactly, so we can think about it as, and this is actually how I did things to start with. I did like A, B, B, A, like that.
Yeah.
I just set these equal, and I said, oh, okay, so A has to be equal to ux, has to be equal to vy, and B has to be equal to vx, which has to be equal to uy. And there you go. Those are the Kosher-Riemann equations for the hyperbolic calculus. Same as the Kosher-Riemann equations for complex, but no minus.
Ux equals by.
It's the same as these, just without the minus. Sorry, I can't write down they're worth anything. But now, I will say, like, if you have an algebra where you're where it's not convenient to make one of the basis elements,
Yeah.
then sometimes it's helpful to use what I call the symmetric Cauchy-Riemann equations. So the symmetric Cauchy-Riemann equations you can get from doing something like the following, just basically saying, well, I'm just going to do df of EI times EJ is equal to, oh, curses. Sorry, I got to start right. So I'm going to assume, this is one of those places where I'm going to assume commutative, just for the sake of, well, I guess I don't have to. I better, commutative for a second here, okay? So suppose EI star EJ is EJ star EI. Right? At least it's commutative on the basis, then that would be enough for what I'm about to write. Then if we have df of EI star EJ equal to df of EJ star EI, well, the thing is, the differential of EI is literally partial f partial xi. And the differential of EJ is nothing more than partial f partial xj. This is the kind of thing I define carefully. And so these are the symmetric Cauchy-Riemann equations. As an application of those, let's look at the Cauchy-Riemann equations of B. Remember we had B was the R cross R algebra, the direct product algebra. So if you had F is say F1, F2, suppose that's your function from B to B, you can ask, okay, what does it mean for that to be differentiable? What conditions, if any, does that place on the component functions F1 and F2? So, okay, great. So then partial F partial x1 times 0, 1 is equal to partial f. I guess I should be using y, right? I mean x and y. So partial f partial x, partial f partial y times 1, 0. So there's like 1, 2, 2, 1. And that is what? So that's, I guess at this point I need to break into scalar notation. Like that actually, at the level of vectors, like there you go. I mean, that's the vector form of them, but that's not really what I want. That's not what I'm after here. What I'm after here is, so if we let f equal to, oh, I already did, f1, f2, right? So this would be partial x f1, partial x f2, I need more chalkboard. This is what? 0 partial x of f2 equal to partial y of f1, 0, right? So we get two conditions. We get partial f2, partial x equal to 0, and we get partial f1, partial y equal to 0. If I flipped back to the UV notation we were using earlier, it would look like Vx equals to 0 and Uy equals to 0. If you wanted to make the transition to the Cauchy-Riemann equations that I have been just using for the previous two examples more natural, I kind of flipped notation on you here. Sorry about that. So what does this say? Like, what does it take for a function to be differentiable? I mean, we're looking at it right here. What does it take for f equal to f1 at comma f2 to be differentiable?
That the partial of f1 is equal to F1 of partial F2?
F1 is...
No, that wouldn't make sense to me.
So here I'm about to use some like standard abusive notation from physicists. Like when a physicist wants to say something's just a function of x, right? To be like f equals to f of x. You know, so if I would say f1 is f1 of what? Well, it's not a function of y.
Function of x.
It's just a function of x in that sense. And f2 is just a function of y. But that's it. So for the direct product algebra, if you have a function whose first component is just a smooth function of x1, and the second component is just a smooth function of x2, that's B-differentiable. So the direct product algebra really doesn't put much limitation. I mean, essentially, functions are B-differentiable if they're basically a pair of smooth functions. There's really there's not much to say there. In contrast, of course, if the function is complex differentiable or hyperbolic differentiable, there's this really interesting intertwangling of the real and imaginary components, the u and the v components. These are coupled through these equations. And the hyperbolics are coupled through these equations, right? And every algebra gives you a different set of Kosher Riemann equations. But it's more than that. Like, that's just the start of it. There's further differential consequences. Like, if you have these equations met, the u and v also have to solve what are called the Laplace's equation. Did you guys solve Laplace equations in differential equation?
Yeah, Laplace's. No, Laplace's equation.
I think you use the Laplace transforms.
Yeah.
Laplace's equation, the Laplace equation is this thing. So this is Laplace's equation. So in one of our future meetings or in your reading, I'll explain to you how we can also understand that there's not just Cauchy Riemann equations. They're what I call the A Laplace equations. There's higher order differential consequences. And there's actually a general principle which is very, very simple, which is essentially this. Any equation that you have in the algebra, it gives you a corresponding differential equation for the functions of the algebra.
Say it one more time.
Any equation in the algebra, there's a corresponding differential equation for the functions of the algebra that they must satisfy. So like this one here.
So if we had an equation of f1, f2, that means both f1 and the functions of f1, f2 would also be...
Yeah, I mean, in some sense, there's kind of an empty result of that in this example, in the sense that they're...
Beta would mean a function of f1, f2.
Right, but my point was here, the restrictions on f1 and f2 are nothing.
Yeah.
Because essentially this algebra is just a pair of reals. Complex, on the other hand, the different parts of the algebra are meaningfully interacting. And so like this Laplace equation, I can understand as the differential version of 1 times 1 minus I times I equal to 0. XX, YY. Like in the hyperbolic numbers, 1 times 1.
Yeah, but 1 times...
Oh, I should have plus here.
Yeah, there it is.
I should have a plus, thank you. So, but in hyperbolic, I need 1 minus j times j, right?
Yes.
In fact, that is 0, and it translates, as it turns out, through all the... I mean, this is not immediate. I'm giving you a fuzzy principle. I prove these things. This actually ends up giving you... This is the analog of the Laplace equation for hyperbolic numbers. XX minus YY equal to 0. But anyway, we'll talk more about this when we meet again. Now, so just to give you a, I am amazed.
Oh, that's because they kept going in and out.
That is, I mean, I can't believe it just finally went out.
No, but think about it, it's been turning on and off.
Oh, I see. So it's just a testament to the instability of electrical. But Okay, so like my battle plan, generally speaking, for this subject is to try to understand calculus 1, calculus 2, calculus 3, differential equations, how the standard results in all those courses transport, I mean, how are they changed, if at all, when we replace real derivatives with a derivatives. I also am especially...
The chain rule wouldn't essentially work the same way.
Is there a chain rule?
Is there a chain? Oh, yeah.
Right. Is there linearity? Is there a product rule? Is there a quotient rule? Like what? I mean, all those things.
So would we have to solve it in terms of like the original quotient, or like the f of x minus f of x plus h over f of x?
Well, you say over, but we don't know what over. I mean, we have to be careful. We can only divide by certain things. But you notice here also another question. I've defined differentiability in terms of right linearity of the differential. Mm-hmm. There's a whole other class of literature where they define differentiability by a difference quotient, where they just take the difference quotient over the elements which have inverses. So it's a kind of funny, like they'll take the limit, I've lost my picture, but like for the hyperbolics.
Yeah, I remember the x.
For the hyperbolics, like if they take a point, well, they're going to like take, if they're looking at that point, they're going to take the limit as you approach that point from all directions except for the zero divisors. They just ad hoc throw out the zero divisor directions and just approach from all other directions. And the reason they do that is to avoid discussion of this stuff, because then they can make it look more like just plain regular calculus with a difference quotient. So one of the other things I do in that paper is I discuss the distinction in those notions of differentiability. And I show how they're different and the same in a wide class of examples. That's kind of heavy lifting. There's a lot more I have to tell you, but I wanted to tell you one of the larger goals before I left here. So like I said, to understand extensions of, and like I've told you before, but I would say most of Calculus 1 has been done, most of Calculus 2 has been done, a big chunk of Calculus 3 has been done. I have done a lion's share of differential equations. Mm-hmm. However, the Laplace transform is something that is not settled. And I brainstormed with students about that about 3 or 4 years ago, and we found some things, but I don't know where those things go. That's a direction you could fiddle with if you wanted to. I'm not sure if that would be productive or not, but it's something, if you like Laplace transforms, we could try to look at that. I just remember that just now. But there are just so many directions you can go. What does the quadratic equation look like in one of these algebras? Like, how do you solve it? That's actually sometimes a very difficult question. There are many, many algebras to look at. It's interesting to understand isomorphisms between the different algebras to a certain extent. There's also a larger issue of abstract algebra. Like a lot of the examples I'm most comfortable with are what are called semi-simple algebras. They don't have what are called nilpotent elements. Nilpotent elements are essentially zero divisors unto themselves. So if you could look at 2 by 2 matrices of the form, or 3 by 3 matrices of the form this. You can prove that the set of all matrices of this form is an algebra. You can add them, you get the same thing. You can multiply them, you get the same thing, right? But one of the things you might notice here is if you let k equal to, say, 0, 1, 0, 0, 0, 1, 0, 0, 0. I don't think it's unital. I'm sorry, Audric. I think I have to throw in things on the diagonal to get it to be unital. So I should add things. I don't know. Whatever. Alpha 1, alpha 2. Pick your poison. There's something on it, because the identity matrix is going to be the 1 in this algebra. But this element is a pesky element, because k times k, well, k cubed is equal to 0. k squared, it's the matrix that has 1 in the upper diagonal element and it's 0 elsewhere. So this k is what's called a nilpotent element of order 3. And the theory of nilpotent elements is more divorced from your experience than some other things. They're quite manageable. They actually have a very strong and nice structure. And I had a student, Nathan, who's actually written like 3 papers beyond mine. He tried to do like pre-calculus of this stuff. And so he spent a lot of time thinking about nilpotent arguments. I don't understand everything Nathan did because Nathan is interested in category theory, and some of his argument techniques I'm not comfortable with. But there's merit to what Nathan did, but I think that could be cleaned up, simplified as well. But, okay, so anyway, I'm just trying to tell you a lot, like my best results are for non-nilpotent elements, algebras that don't have nilpotent elements. There's like a wide class of algebras, semi-simple algebras. You'll see that as you read this paper I've been dancing around. Finally, one of the larger goals for this whole work is to apply it to solve interesting systems of partial differential equations. So you start to see these Kosher Riemann equations, right? And I started to tell you there's also something called Laplace equations, right? And you could look at other differential consequences of those, all right? And then the following question I think is an interesting one. If you're given a system of partial differential equations, right? Is it possible to take that system of partial differential equations and recast it as one or more just algebra differential equations?
Like abstractly?
Right.
You really think that a partial differential, you can write in a partial differential equation that could work across a wide variety of abstract algebras?
No, I think that there's a very special subset of partial differential equations which can be solved in this manner. For example, shnikes. Just a second, I gotta look it up. All right, here it is. So suppose you had partial u partial x was u squared plus v squared. And partial v partial x was um, 2uv. So I can solve this system by making an appropriate algebra substitution. Now, admittedly, this is a relatively simple one. So like I've tried posting this on the Stack Exchange before and seeing how long it took the differential equation minions that lurk about there to solve it. And it was solved within like 10 minutes. Like they just...
You say u prime, v prime. Oh wait, no, that's partials. No, you can say that.
Yeah. Let's see here. But there's more. It's also paired with ux equal to vy. And uy equal, anyway, so these are that's kind of the dead giveaway for my example, but so here it is. If you if you have partial z of u plus jv, that is partial x of u plus jv. That, as we go on, what I'll teach you is that to differentiate with respect to the algebra is to differentiate with respect to x in the corresponding real version of it, assuming that the identity element's the first element. But, okay, so that's, you know, ux plus jvx, right? And ux was what? It was u squared plus v squared, right? And that was j times what? 2uv, right? So if we call this...
Oh, and then could you say partial u, partial x right there?
We can call just, well, yeah, I traded it for the u. I traded it for this equation.
Gotcha.
Yeah, and I'm going to call this thing w. So what we have is we've got dw dz equal to, what's this? Well, this is really u plus jv times u plus jv. See, that's w squared.
Oh, yeah, it is.
So this is w squared. So then, using calculus 1 or 2, or differential equations, dw over w squared is dz. Separate variables, integrate both sides, minus 1 over w is equal to z plus a constant, which gives us that w is minus 1 over z plus c. So I'm working in the hyperbolic numbers. I'm making a hyperbolic substitution. And if you work this out, well, this is minus x all right, so let me break it out here. This is 1 over x plus c1 plus j times x plus c2, right? And that's going to give me x plus c1 minus j times x plus c2 divided by x plus c1 squared minus x plus c2 squared. And there's a minus overall. And that's equal to u plus jv. But you see that equation right here? See this? This right here?
Yeah.
If you equate u with the real part over here, you get u is equal to like x plus c1, parentheses with a minus out front, divided by x plus c1 squared minus x plus c2 squared. And v is, well, x plus c2 over, oh, I meant to say y. There's a y. I'm an idiot. That's y. I can't do math. Y. Y. Y goes with the c2. I'm using that formula for the inverse and the hyperbolic numbers we talked about an hour ago. But if you look at it, those are in fact the solutions to this system of differential equations. So I took the partial differential equation, I converted it to an ordinary calculus equation in the hyperbolic algebra, solved it using, you know, elementary stuff, and out pops solutions to the original PDE. Now, you know, there's going to be a very special class of PDEs which are amenable to this kind of solution. But that's one of my questions, is like trying to understand which systems of partial differential equations can be solved using some algebra substitution.
My question is, like, remember how when you talk to certain algebra people that, like, they'll say that, like, if they're isomorphic, they're the same.
Uh-huh.
If you can only transcribe these to, like, isomorphic algebras, couldn't you just say that's a class of algebra?
Oh yeah, there's going to be more than one algebra that works.
I know that, but what
Yeah.
I'm saying is like if they all isomorphic to each other, wouldn't that just be a class? Or if they all like kind of like come down to one, wouldn't that just be like a class of algebras that could all be represented by the one?
Maybe. I mean, I look for that kind of thing. I also look for like, like sometimes you find something in the system that's just impossible for the corresponding algebra substitution, But that's a very open-minded, very, very vague inverse question I'm asking. And one of my ongoing works with my colleague in close to Juarez, he's in one of these, state universities of Mexico, is trying to solve the inverse problem stated in a more precise way for particular classes of PDEs. It's like if you fix the PDE you're looking at to be one of a particular type, then it becomes an easier question. Can we rewrite this as a corresponding algebra differential equation? But Elliott also has introduced something called twisted A differentiability, which adds another wrinkle to this, which I don't have an intuition for. But I'm trying to play nice and finish that work with him. But my heart is with A differentiability because it's just like complex analysis. I mean, everything we're doing here has application in complex, and complex is nicer than these general algebras, like way, way nicer, because complex numbers are a field, which means all this worrying I'm doing about, but you can't divide complex numbers. You can divide, as much as you can divide anywhere. But anyway, that's the start. Now, so it'll take a while for you to get accustomed to like what has already been done. Yeah. But hopefully along the way somewhere we'll find you a question. That's my hope.
All right.
So just keep that in mind as you're reading. And I'll send you a link.
Okay.
But as you're reading the first paper, just write yourself questions and bring me back questions, and we'll try to go from there. That's like the best thing. Well, I'm gonna be late for supper, but I think it's for the best. I think if I'd left here when I was threatening to, I would have driven into something unpleasant. Now, did you want me to post these?